Until now, we have talked about um, closed systems primarily. We have applied energy balances onto closed systems as well, and we know that for closed systems, work and heat can be exchanged, and obviously we can apply the first law of thermodynamics onto it. Now, though, we are going to move on to open systems, and we already talked about this, that open systems are also called control volumes. So when we're talking about a control volume analysis, what that means is that not only work can take place for that system, heat content can also be exchanged between the system and the surroundings, and the mass uh, then becomes an important quantity as well. So mass can enter into the system, mass can leave the system as well, and we are going to be calling this a control volume analysis. So we could basically apply the conservation of mass principle onto a control volume, right? So to develop the control volume mass balance, let's just look at this figure over here. And what this figure shows is it shows you a system that has a fixed quantity of mass m, which is basically occupied at different regions of time. So when we're looking at time t, let's say we are at a certain time t, and at time t, the mass under consideration is shown in terms of, well, the mass m subscript cv for control volume. So mass that is contained within the control volume. So this boundary over here, the dashed boundary, is giving you the control volume boundary. So the mass that is contained within this control volume plus the mass that is at a small region that is right next to the control volume. Okay, so this is at time t. Let's say a certain time passes, and so let's say if you're at 5 seconds right now, let's say 3 more seconds have passed, so then the time that has passed would be t plus delta t, right? So once this time starts elapsing, what starts happening is that this m subscript I over here, which is the mass within the small region, which is labeled I, this starts crossing into the control volume. Okay, so as time starts increasing, time moves towards t plus delta t, this mass starts moving into the control volume boundary. And as this is moving into the control volume boundary, some of the mass, you can call it m subscript e, it starts moving out of the control volume boundary. Okay, so it's important to understand here that the mass that is entering into the control volume is not necessarily equal to the mass that is leaving the control volume, because obviously the if let's say we call this an inlet and we call this an exit, then this inlet and exit diameter, let's say, can be different. So then more mass can move into the control volume and less mass can exit the control volume, right? So if I was to basically write the total amount of mass expression, so the total amount of mass is going to be still constant, right? In terms of, let's just look at what is happening at from time t to time t plus delta t. On one hand, we have mass within the control volume, right? Plus mass at region I. And all of this entire thing should be equal to basically the mass of control volume, right? So this is at time t. This is mass contained within the control volume at time t, plus mass in this region m. I. This should be equal to mass of the control volume at time t plus delta t plus the mass that has basically exited the control volume, right? So the total amount of mass is going to remain constant, but that doesn't mean that mi is going to be equal to me. Sorry, just forget about this. It's m subscript e. Or I could rearrange this and I could write it in terms of basically, if I was to move this term onto that side, it would become mass contained within the control volume at time t plus delta t minus mass contained within the control volume at time t, and all this is going to be equal to mass in region that is being represented by E minus, or actually the other way around because this is going to go onto that side, so it's going to be Mi minus Me, right? Because you're moving this onto this side, you're moving Me onto this side of the equation, so Mi minus Me. And now I could just go ahead and divide this entire equation by delta t, right? So I could divide the left side by delta t if I want to express it on a time rate basis, and I could divide the right hand side by delta t as well. So mi divided by delta t minus me divided by delta t. And if I basically use the limit function here, and if I limit basically delta t, so I apply the limit where delta t approaches 0, right? So if I apply this limit onto this entire thing, then the left-hand side of the equation would become a derivative. So it's going to be derivative of mass in the control volume per time, and that's going to be equal to, another way to write the derivative is in terms of dot. So m dot I minus m dot E. So this is the expression that I get where this term on the left hand side, it basically denotes the time rate of change of mass within the control volume, and mi dot is the inlet mass flow rate, and e dot is the exit mass flow rate. Okay, so this is called mass flow rate. What else? If I wanted to write this in terms of a statement, I could write it in terms of basically time rate of change of mass that is contained within the control volume at time t, like I already said. And this would be equal to time rate of flow of mass in across the inlet I at time t minus time rate of flow of mass out across exit E at time t. Okay. So if this was an instantaneous process, then obviously time t plus delta t would be approaching time t. That's why it's written like this in the form of a statement. Another thing that we need to remember is that if, let's say, there's obviously a system could have more than one inlet, so it could have, let's say, multiple inlets and outlets. So to account for that, the equation that I just wrote, I could write it in terms of, so the equation that I wrote was of the form, basically, time rate of change of mass contained within the control volume at time t, and I equate this to mi dot minus me dot. And if now there's more than one inlets and more than one outlets, so then I would have to sum up all the inlets. I would have to sum up all the mass flow rates across the inlets. So then I would just write the summation sign over here. And minus, again, I would have to write the summation sign here as well. This is E. There's a minus in the middle here. So I would have to sum up mass flow rates across all inlets minus mass flow rates across all exits. And the quantities here, mi dot, me dot, they denote time rates of transfers. In SI units, mass flow rate is in terms of kilograms per second. So basically m dot is in terms of kilogram per second. So this expression over here is called the mass rate balance for control volumes, and it is applicable for several inlets and exits. This statement over here, written in the form of words, this is called the conservation of mass principle for a control volume. Yeah, so just remember that this is the mass rate balance, and m dot represents the mass flow rate, and the units for this are given in kilograms per second. But just by looking at m dot, we can't tell what it means, so we need to find out m dot in terms of, let's say, velocity, or in terms of density, in terms of area maybe. So we need to evaluate an expression for m dot here. So to do that, let's just look at this example here, that we have fluid, let's say, or a system where we have, let's say, a certain area A. So what we do is that we consider a small quantity of matter within, a small quantity of mass within this area that is flowing with a velocity v, and this velocity v flows across the small incremental area dA in time interval delta t, right? So, but this velocity over here, this component v delta t, this is can basically be distributed into two components, into its normal component and the tangential component. So the normal component would be the one that would be in this direction, basically in the direction of the flow. So it would be perpendicular to dA over here. What else? Yeah, so if I was to find out the volume of the mass that is crossing this incremental area dA during the time interval delta t, then I could write it in terms of basically, so if I was to write down the volume, let's represent volume like this, v dash, so the volume of mass would be equal to basically the product of area into its altitude. So the area is going to be equal to dA for this incremental one, and I can multiply it by the altitude, which would be the component of the velocity in the normal direction multiplied by delta t, right? So this is going to give me the volume of the mass that is crossing dA during the time interval delta t. And if I was to convert this into mass now, because I want to find out the mass flow rate, so I need to find out the mass first. And I already know the relationship for mass, density, and volume. So in order to do that, I would have to just multiply this entire term on the right-hand side with density, right? So if I multiply this entire thing with density, I would get mass, right? So let me just write this here. Rho into Vn delta T dA and this entire term over here is volume V dash. And we already know that density is basically equal to mass divided by volume. So then if I'm multiplying density over here into volume, then that would be equal to mass, right? So this entire thing would be equal to the amount of mass that is crossing dA during the time interval delta t. Okay, so that's on this left-hand side. Amount of mass crossing dA during the time interval delta t. And now if I was to divide both sides of this equation by delta t, so and then I take the limit as well, so if I apply the limit, let's say I'll just write it here, apply the limit, so that delta t approaches 0, and I divide this entire thing with delta t. So this is the amount of mass over here crossing dA. So this is kind of like what we just saw previously in terms of when we wrote this mass crossing into control volume divided by dt, kind of like that. So then this would be on the left hand side, this entire thing would become the instantaneous rate of mass flow across dA. So instantaneous mass flow rate across dA, and I could write it in terms of m dot, could call it m dot, and then m dot would be equal to, so because I divided both sides with delta t, this would cancel out, so it would be, I'd be left with rho v subscript n into dA, and I apply the integral over all of this, and that would give me m dot in terms of the integral across the entire area, and this integral is being applied on rho vn into dA. So this is the equation for mass flow rate in terms of an integral, and this can be applied at the inlets and the exits to account for the mass flow rates into and out of the control volume. But the thing is that this equation over here is a bit complex, and we need to simplify this equation in order for us to apply it onto some kind of problem that we consider. So the way that we do is just remember this equation over here, and so m dot is equal to rho v n, v subscript n, which is velocity, into dA, and integral over the entire thing. So in order for us to simplify it, what we do is that we go to the one-dimensional flow model, and what the one-dimensional flow model means is that it's an idealization, it's an ideal model, ideal sort of model, and the flow is called one-dimensional if it fulfills two conditions. The first condition is that the flow is basically normal to the boundary at the location where mass enters or exits the control volume. So because the mass is entering the control volume here, so it has to be perpendicular to the cross section here. So this is the cross section. If I was looking at it in basically, let's say 1D, what would happen is that this would be my cross section, right? So I'm just, you can see it in 3D right now. I'm writing it in 1D or representing it in 1D here. It's the same inlet. It has the same area over here. And basically, air is entering into this inlet. as a perpendicular to the area. Okay, so the flow is normal to the inlet boundary, and the flow has to be normal at the outlet boundary as well. That's the first condition for idealization of the 1D model. The second condition is that all the intensive properties are going to be uniform with position over the inlet or the exit. So what that means is that the velocity, although it may be changing on a microscopic level, but as a whole, we just assume that the velocity or the density or all the other intensive properties stay uniform, and we have one single value for all of these. Okay, so it may be varying on a microscopic level. The velocity could be, let's say, different here and different over here within the pipe, because we're looking at a pipe right now. It could be different over here, but what we're assuming is that no, that is not happening. We have a uniform velocity. So we have, if let's say the velocity is 5 meters per second, then the velocity is 5 meters per second over this entire inlet. Okay. So all the intensive properties have one single value. Okay. So if that is the condition, then the equation that we previously saw for m dot in terms of the integral, now the area is A, so I could write it in terms of rho A v. Okay, so because the velocity has one single value, the density would have one single value as well, and the area is being represented by A. So I could write m dot in terms of rho A v, where A is the area, V is the velocity. And this is the mass flow rate for the one-dimensional model. I could also write m dot here in terms of specific volume, because specific volume is the inverse of density, so I could write it in terms of A v divided by small v, which would be specific volume. Make sure you remember that this is actually velocity, okay, so it's in meters per second, and this is specific volume, small v. So m dot could be written in terms of this. This over here is obviously mass flow rate. You could also verify the units here now. Check the units. It's going to be in terms of kilogram per seconds. And another important thing to know here is that this product here, area into velocity, this is actually called volumetric flow rate. Okay, so area into velocity is called volumetric flow rate, and this is basically in terms of so what would be the units of this? Could you work it out yourself? If you multiply area into velocity, so it's going to be meters square into meter per second, so the units are going to be meter cube per second for volumetric flow rate. Okay, so this term over here, this equation represents the mass flow rate. The product AV within this equation represents the volumetric flow rate. And basically what we can do is that now we can substitute the equation that we saw previously in terms of basically mass flow across the control volume divided by dt. That was equal to m dot I minus m dot E, or the summation one as well. So if I was looking at multiple inlets and outlets, then summation across, because I had m dot I over here, so m dot I could replace by this expression, and I could write it in terms of, let's say, the area of the inlet, the velocity at the inlet, divided by the specific volume of the fluid at the inlet, minus, again, summation of mass flow rates at all the exits, so m dot E, and I can replace this by area of the exit multiplied by velocity at the exit divided by the specific volume of the fluid at the exit. Okay. So then I could use this equation as well. And let's say if I was to simplify this even further, if I was making another idealization, which is called a steady state idealization, what that means is that if I'm talking about steady state means that no properties are changing in time. And if no properties are changing in time, then what that means is that the total amount of mass that is present at any instant will remain constant. And what that means is, so this is the general equation, and if I apply the steady state form onto it, where all properties are not changing in time, then this left hand side would go out. This would be equal to 0. And what that means is that the total incoming and outgoing rate of mass flow, the total incoming and outgoing mass flow rates are going to be equal to each other, right? So mi dot is going to be equal to me dot, or the summation over it. This is only a special case though. This is the steady state form. Okay. The previous equation, this equation, this is the general form. This is obviously used, but if we're making another assumption, because we already made one assumption that we are talking about one-dimensional flow. This is the second assumption, that if we are talking about a kind of flow where basically no properties are changing in time, that means that the total amount that remains present at any instant within the control volume has to remain constant. So then this term goes out and mi dot becomes equal to me dot. And now we can just take a look at an example. So the example question is that we have a feed water heater, and the purpose of a feed water heater is that you're supposed to heat up the liquid that is present within the feed water to a higher temperature. Okay, so let's just look at this example here. So we have a liquid at state 2. So at inlet, so we've got 2 inlets first of all, and we've got 1 exit. We've got inlet at 1 and inlet at 2, and we've got the exit at 3. What else? So at inlet 1, we've got water vapor that enters at a pressure of 7 bars and a temperature of 200 degrees. The mass flow rate is given as well at inlet 1. And we've got at inlet 2, we've got liquid water, it says. So we've got liquid water at this pressure, 7 bars, and temperature equals 40 degrees. And we've got the area given to us as well, 25 centimeters square. So what is the purpose of a feed water heater? We've got a liquid entering here, and we want to heat it up. So it's at 40 degrees right now. We want to heat it up so that when it leaves at or exits at state 3 here, it would have a higher temperature basically. So what else is given to us? Okay, so at state 3, at state 3, it's given to us that the water is in the form of a saturated liquid. It's at 7 bars, and we've got volumetric flow rate given to us. So volumetric flow rate, we know it's in the form of A multiplied by V, area into velocity. What we need to find out is the mass flow rate at inlet 2 and the velocity at inlet 2 as well. Okay. All right, so first of all, we have to write that equation that we saw. the general equation, which is of the form like this, is equal to, so because we said that there can be multiple inlets and multiple outlets in the form of summation, so right now we've got 2 inlets. So if we sum it up, it would be basically m dot 1 plus m dot at state 2 minus m dot at state 3. So we are making an assumption here that this operates at a steady state, and because of that, this is going to be equal to 0. So we can solve for m dot, let's say, at 2 in terms of m dot 3 minus m dot 1, right? So what I did is that I took this onto the other side, m dot 1 onto the other side, so m dot 2 is equal to m dot 3 minus m dot 1. And why did it do that? Well, because m dot 1 is given to me, and I can calculate m dot 3 over here. So m dot 1 is given to me, it is 40 kilogram per second. And to find out m dot 3, what I will do is that I will, because I'm also making the assumption that this is a 1D flow, so I can write it in terms of area into velocity at 3 divided by the specific volume at this state at 3 at the exit. So this is already given to me, area into velocity 0.06 meter cube per second. I need to find out a specific volume here at the exit. So how am I going to do that? Well, it's given to me that the liquid is of a saturated form, and the pressure is given to me as well. So because it is saturated, that means that I have to go to the saturated water table. And the saturated water table is table A3, right? So I go to table A3 and I go to 7 bars, and across 7 bars, because I'm looking at a saturated liquid, so the saturated liquid, for the saturated liquid, the specific volume here is going to be equal to 1.108 multiplied by 10 to the power minus 3, right? That is what it's going to be equal to, and this is in meter cubes per kilogram. Okay, so all I have to do is then I can just plug it in here. So equal to 0.06 divided by 1.108 multiplied by 10 to the power minus 3, and I can find out the mass flow rate at state 3, and this is going to be equal to, you can work this out yourself too, it's going to be equal to 54.15 kilograms per second. So now that I've found the mass flow rate at 3, and I already know mass flow rate at state 1, so I can basically go ahead and, hold on, let me just get this. I can work it out, right? So m dot 2 is going to be equal to 54.15 minus 40, and that's going to be equal to 14.15 kilogram per second. So I found out the mass flow rate at inlet 2, and now I need to find out the velocity, right? I need to find out the velocity at inlet 2 as well, and I can use this same expression just like this. I could write m dot 2 in terms of basically the area at 2 into velocity at 2 divided by the specific volume at 2. And if I just rewrite this equation in terms of velocity, because that is what I have to find out, I could write it as m dot 2 multiplied by a specific volume at 2 divided by area at 2. So the only thing that I don't know right now is the specific volume here. And how can I find that out? Well, I've got pressure given to me. I know that it's liquid water. I've got pressure given to me, which is 7 bars. And I've got temperature given to me as well. So I would have to go to the tables and see across pressure of 7 bars what is the saturation temperature. And if the saturation temperature is higher than the given temperature, which is T2, then that means that the water is of a compressed liquid form, okay? And that is the case. If you go and check it from table A2, or actually A3, because that is the pressure table, so across 7 bars, go and check what the temperature is. Okay, the second column, across 7 bars. See in the second column what the temperature is given to you. I think it's 165 degrees or something like that, 165 degrees Celsius. And obviously that is greater than the temperature that is given here, which is 40 degrees. So that means that liquid water is a compressed liquid water. And for a compressed liquid water, we've already discussed that to find out this specific volume, we can just go to basically the saturated liquid table that is of the temperature form, and we just take out the value of VF, which is the saturated liquid specific volume. So we go to table A2, and at table A2 across 40 degrees, in the third column, I can just pick out this value, 1.0078. This is the value for specific volume, and I have to obviously multiply it by 10 to the power minus 3. And all I have to do is I just plug it in here. So m dot 2 is 14.15 multiplied by specific volume, which is 1.0078 into 10 to the power minus 3 meter cube per kilogram, divided by area, and this is 25 centimeters square. Also make the adjustment, convert it into meter square first, and I will get the velocity at state 2, which is going to be equal to 5.7 meters per second.